Alright everyone, welcome back. Now I am going to go through this video assuming that you saw my last video on gas laws, and we're going to combine all of those gas laws to make what's known as the ideal gas law. Now several times I've been using the word ideal gas. Now the term ideal gas refers a lot to a gas that follows certain circumstances that we just are going to assume for all that. Those are, well, let me explain it this way. So say you have a box. Now that box is filled with a gas. And so what we're going to assume is that the individual particles that make up the gas are free moving. They take up no space in it of themselves. So the particles have no volume, but the combined pressure of the particles is what creates the volume. And so they flow around in whatever direction. They bounce into each other, and that's what creates the pressure. However, they are not in any way polarly attracted to one another or non-polarly attracted to one another. They are completely indifferent to one another. They just hit each other randomly and continue flowing about freely. So, with that in mind, as to what an ideal gas is, let's start combining these equations. Now there's actually quite a few ways to combine them to get the ideal gas law that we want. So I'm just going to show you one of the ways, and then if you want to continue studying to see exactly how it all works, you can try and find some of the other ways that you can combine them to get this ideal gas law. And so what I'm going to start with is by taking the law that we discussed in the first one of P1 times V1 is equal to P2 times V2. So, Boyle's law. Now, I'm going to look at this pressure value and attempt to substitute it for something else. Well, I'm going to go down to the next equation, where P divided by T is equal to K A. Now what I'm going to do is multiply both sides by T, and so what we get is this going on. And now I'm going to say that this is equal to P2. And so I'm just going to plug this in, and what we get is something that looks like is equal to Ka times, oh, not P, times TV2. Now I'm going to try and substitute this volume in for something else. Now what we need to do is we need to get moles. So we have two equations that has moles, and one of them has volume. So I'm going to use the one that has volume. And so what we have is Gay-Lussac's law, where V divided by number of moles is equal to Kg. So I'm just going to rearrange this equation. So we get n kg, and now when I plug it in up here for that V value, what we simply get is an equation that will look like P1 times V1 is equal to Ka times T times the wonderful looking equation that I just devised, which is Kgn, n being the number of moles. So what I'm going to do is multiply Ka and Kg together, and that is going to give us a new constant, which I am going to call R. So R is a constant. And then I'm going to move n way over here. And so what then we get is P1. Well, I'm just going to drop the ones now because we don't need them anymore, because there's only one pressure and one volume in the equation now. So one P value, one V value is equal to n times that constant times T. This is what's called the Puvnert ideal gas law. We call it Puvnert just because that's what the letters spell out. This law does not actually belong to anybody. So you can call it the Lord Vaskin law, because it's just cool like that. Now, this is an amazing gas law. Now, what we have is R is that constant, and everything has units in this. And so what those units are is, if we put pressure as a unit of atmospheres, volume as a unit of liters, and then we have on the other side of the equation, moles is always in the unit of moles. You could put it in the unit of atoms, but for simplistic reason we're going to put it into a unit of moles. Then we have our R constant, and then we have temperature is in Kelvin. Now, here's something to remember for all ideal gases. The temperature must be in Kelvin. Now, if you're in Fahrenheit, Fahrenheit has a 0 in it. That is a little bit below freezing point. And also in Celsius, we have a 0 in it. Look what happens to the equation if we plug in Celsius and we're dealing with the freezing point of water. But you see, neon is still a gas at that state. Neon acts as an ideal gas at the freezing point of water. And so, how can we figure out the pressure of neon or the volume of neon? Because this whole side of the equation will go to 0, and that would be bad. So we use Kelvin, and Kelvin then is written in terms of K, and it's just simply the temperature in degrees Celsius plus 273.15. And that's the temperature in Kelvin. Simple enough? Think so. And so we just have it in terms of Kelvin. There is no degree sign here. Do not put a degree sign above the Kelvin symbol. And so what we need is our value, our constants. Well, our constant R needs some values to make everything look nice. So I'm going to give you what that constant of R is. It is 0.08, I want to say it's 306. I had it written up here at the beginning of the video. It was written down here at the beginning of the video, so trust that value. Of course, I can just pull it up real quick. Oh, it's 2. So it is 2 here. Do not follow the 3. It is 2. Now it is liters times atmospheres divided by mole Kelvin. That is the units for it. So, I hate it when this happens. So these are the units for this value of R. Now, if you change any of those units out, you need to go through a conversion. Now, those conversions are just a simple conversion factor, which you should be able to use by this point. To be able to convert, say, atmospheres into bars is a 1-to-1 ratio. So then that one's easy, so that's the same R value. But if you want to convert to like torr, then you would have to do some math. But you could just look it up online. That's what I always do. And then figure out what that R value is if it's liters times torr over moles Kelvin. But in the standard version, you will see this equation. It's liters times atmospheres per mole Kelvin. And we use atmospheres for pressure, liters for volume, moles for moles. R value is, well, right here. And then temperature in Kelvin. Now, the temperature can only be in Kelvin. Pressure can change out. Moles can change for number of atoms, and volume can be in liters. It could be in gallons if you really want, but we tend to stick with metric when it comes to science, and it can be in milliliters, kiloliters, whatever floats your boat. But this is the standard way of doing it. And so that is the ideal gas law. I think it is quite nice. And with that, only a few more videos in my general chemistry discussions, and then I'm going to start branching off into the specific types of chemistry values. So stay tuned. More videos coming at you soon.